Hi class, welcome to the second video for our synoptic meteorology class. In the previous video, we talked about adiabatic lapse rate, atmospheric stability, but have you asked, how do we derive the adiabatic lapse rate? We will be able to understand adiabatic lapse rate when we have a greater understanding of the hydrostatic balance. In this video, we'll talk about just that, the hydrostatic balance, and how do we come up with the hydrostatic equation. So first, when we are talking about hydrostatic balance, we relate it to air pressure. So what's air pressure? From your previous lessons, air pressure at any height in the atmosphere is due to the force per unit area exerted by the weight of all the air lying above that height. Consequently, this atmospheric pressure decreases with increasing height above the ground. So consider this diagram that I'm showing you. We have here four people standing shoulder on each shoulder. The man at the top says, "Up here, I have little weight on me. I feel low pressure." But the man below says, "Down here, there is lots of weight on me. I feel high pressure." You can remember that traces of atmosphere can be detected as far as 500 kilometers above the surface of the Earth, but 80% of the atmosphere's mass is actually contained within the first 18 kilometers from the surface. And again, air pressure can be measured, or atmospheric pressure can be generally measured in millibars. Other units can also be millimeters of mercury, ATM, hectopascal, or PSI. Hydrostatic balance just means that the net upward force acting on a thin slab of horizontal air due to the decrease in atmospheric pressure with height is generally very close in balance with the downward force due to gravitational attraction that acts on the slab. Note that it says here very closely in balance. So the upward force versus the downward force is closely in balance. So that's basically what the hydrostatic balance means. If the net upward pressure force on the slab is equal to the downward force of the gravity on the slab, the atmosphere is said to be in hydrostatic balance. So this is what I mentioned a while ago. The forces acting on a slab, either upward or downward, is in balance. So let's consider this clearer diagram of a thin slab of air. So when we say thin slab of air, we are talking about this gray area here. Okay, so the mass of air between height z and z plus delta z, so this one, talking about this one, in the column of air is the density delta z. And so we can see the forces here acting on that slab of air. The downward gravitational force acting on the slab of air, let me just underline that, downward gravitational force. So acting on the slab of air due to the weight of the air is given by gravity, density, and delta or delta z. So this is what we're talking about. And so let the change in pressure in going from height z, this one, to height z to dz, be delta p. So note that we have a negative sign. There's a negative sign. Negative sign denotes because we know that the pressure decreases with height, so we put the negative sign in there. And so, knowing that, the upward pressure on the lower face of the shaded block, we are talking about this. The upward pressure on the lower face of the shaded block must be slightly greater than the downward pressure on the upper face of the block. So why is that? If the downward force is, or if the downward pressure is greater than the upward pressure, then the air parcels or any air will be prevented to move vertically. So there will not, so clouds will not be able to form. There will not be precipitation as well. Therefore, the net vertical force on the block due to the vertical gradient of pressure is upward because of the pressure gradient force. So we talked about this in the previous video. So what is this? For a slab to be in equilibrium, its weight must balance the pressure gradient force. So again, the weight balancing the pressure gradient force, which is acting, which is pushing the slab of air up. And so, for an atmosphere to be in hydrostatic equilibrium, the balance of forces in the vertical requires that the negative delta P and this one, gravity density, and delta Z should be equal or balanced. There should be a balance of forces in the vertical. So the net upward force, again, acting on a thin horizontal slab of air due to the decrease in atmospheric pressure with height, is generally very closely in balance with the downward force due to gravitational attraction that acts on the slab. So we can do some rearrangements of this equation. So we can see that dP over dz equals negative gravity times the density of the slab of air. Note that we have a change of notation. The left-hand side of the hydrostatic equation, so we're talking about this one, is written in partial differential notation. So why is that? It's because the variation of pressure with height is taken with other independent variables held constant. And again, we can note the negative sign at the right hand side of the hydrostatic equation because pressure decreases with increasing height. And so we know when we talk about hydrostatic equation, we are actually talking about atmosphere equalizing. So I came upon one question from Reddit in our meteorology, and it and one Redditor asked, why doesn't the air pressure equalize around the globe? The question is, hello weather enthusiast. I have a question about high and low pressure areas. I understand what they are and the effect they have on the weather, but I was wondering why the air pressure around the globe doesn't eventually equalize after time. I'm sure it has something to do with gravity and wind and heat, but sometimes the areas of low or high pressure areas seem to occur so randomly. So I want to give this question to you. Why doesn't the air pressure equalize around the globe? So I'll give you 10 seconds to uh, think about your answer. Okay, I hope by this time you are able to have an answer, and I hope that you did not search the internet for the answer. Uh, in this thread, I also got a very good answer. So let's see. One Redditor also answered the question and says there, I mean, the atmosphere is constantly trying to equalize. Hence, the wind moving from low pressure areas to high, which is actually just the pressure gradient force. But because the process takes a long time and the sun heats up surface of the earth, unequally new areas of low pressure are constantly created and the equalization can never quite finish. It's quite interesting that people ask this question, and I believe that if you have an understanding of the atmosphere, you will be able to answer such questions. And so I have a question for you. Question: we took gravity in the hydrostatic equation as constant, right? That's just acceleration of gravity, 9.81 meter per second squared, as constant. But in reality, gravity also decreases with height. So how do we account for that change? In the next video, we'll talk about geopotential as well as geopotential height. So that's what we're talking about in the next video. And if you have questions or clarifications or comments and suggestions, feel free to reach out, and see you in the next video. Bye.